Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the IR spectroscopy, and in that we have discussed the hydrocarbons. In that hydrocarbons, such as hydrocarbon means what? The organic compound which is made by carbon and hydrogen is known as hydrocarbons, such as alkane, alkene, alkyne and the aromatic compounds generally as a benzene, naphthalene, etc. These are belonging to as a hydrocarbons, and if these hydrocarbons and their corresponding stretching frequencies, the particular stretching frequencies are observed at that particular by knowing the absorption peak, because every functional group correspond to specific stretching frequency, and from that the chemist can recognize or identify what type of the functional group present in the unknown compounds. And that type of the discussion we have discussed today. What we are going to discuss yesterday, we have seen hydrocarbons. Today is the second one, which is known as second, let us see as a capital letter B, alcohols and ethers. Alcohols and ethers. Alcohols and ethers. This is the point we are right now discussing. Let me clearly say here or explain alcohols. We know that OH stretching, general formula of alcohols are OH, and another one suppose maybe as a pH, OH, or we can call it as AROH, right? These are the generally alcohols. These are the phenol, as we know that. Phenol and the alcohol are easily distinguished from each other by the chemical test, generally with ferric chloride. Ferric chloride gives blue or green color with the phenolic, and alcohol do not give such type of the color. So by using this reagent we can easily distinguish phenol from alcohols. Other way around we can distinguish between phenol and alcohols. Phenol are acidic in nature, whereas alcohols are neutral in nature. And why phenol are acidic in nature? We know that in the strength of, if you remember third semester chapter number 1, the strength of acids and bases. Acids and bases, there we already discussed about how we can determine the strength of acids and bases, that we are easily determined by using different type of the factors such as inductive effect, resonance effect, then hyperconjugative effect, steric effect, hydrogen bonding, tautomerism. These are the some of the steric factor which can affect the strength of acids or the bases, either acidity increases or decreases, that depending upon these whatever I have just now mentioned here, the factor which can affect that strength. So here phenol, after the dissociation, acidity means after the dissociation which produce the H plus ion, and it means that it shows as a acidic properties. And whenever there is a formation of the conjugate base, and that conjugate base are well stabilized due to the resonance, and due to this reason phenol are acidic in nature, whereas alcohols are neutral in nature. That's there. That is not the point of discussion, but here, and if you remember ether, what do you mean by the ether? Similar to the alcohol, just now we have defined alcohol means what? The organic compound having the general formula ROH is known as alcohol, and ether similarly we can define the definition of that ether, the organic compound having general formula R dash is known as a ether. Let us see one of the simplest example over here which can shows as alcohol. Suppose we have this one CH3, then CH, O and H. Do you know the name of this compound? This is the simplest compound, that is a ethyl alcohol. We can call it as a ethanol or the ethyl alcohol. Ethyl alcohol is a IUPAC name, and whereas ethanol is a IUPAC name, whereas ethyl alcohol is a common name of that compound. Now if you draw another structure CH3, then O, another CH3. Look at here, if you observe these two structures carefully, you will find the molecular formula. There are 2 carbon atom, number of hydrogen atom are 6 and 1 oxygen atom. The molecular formula of these two structures, this you can call it as a structure number first, this will be the structure number second. The structure first and structure second, is there any other structure possible for this? Okay, let it be, this is the structure number first, this will be the structure number second. What kind of the isomer they are? As we know that isomer means what? The organic compound having same molecular formula but different structure are known as a isomer, and that phenomenon is known as a isomerism. And that isomerism further divided into 2 types. Number 1 is called as a stereoisomer, and second one is termed as a structural isomers. And that structural isomer further divided into as a 5 types, such as chain isomerism, position isomerism, functional group isomerism, then tautomerism, metamerism. So these are the 5 type of the structural isomerism. So this is a what kind? This is a structural isomerism. If you see the skeleton of that or the framework of that carbon atom, here are different. In another case is also as a different. The number of atom involved in those structure are identical, same, but the carbon framework or carbon skeleton are different. It means that one is showing as a functional group is alcoholic, another one showing as a ether, and therefore these 2 kind of the structure, even though having as a molecular formula is the same, but the structures are different, so it is belonging to as a positional, it is belonging to as a functional group isomerism. Functional group, as we know that functional group, simplest definition of the functional group is a site of reaction. Site of reaction means whenever we are adding as a reagent, the changes occur at a particular part of the organic compound. other part remains as it is. There is no change at all, but at a particular site only the changes are observed or occur, so that site is known as a functional group. One of the functional group is converted into as another functional group. So if you see here, here is a alcoholic group, functional group is present, and here is a ether. So there are two different functional groups are there, and therefore this type of the structure, the relationship between these two structures are known as functional group isomers. Now here you mainly focus, I am trying to explain, suppose as a question may appear in an exam, the question may be like this: how will you distinguish the following pair by IR spectroscopy? These are the two structure. This is the structure number 1, this will be the structure number 2. Now how would you distinguish, or how will you distinguish these two following structure by IR spectroscopy? And IR spectroscopy, it means that you have to use IR spectroscopy for answering such type of the questions. The answer in terms of you must mention the group frequency or the stretching frequency. Generally IR spectroscopy is known for the functional group. Here always remember functional group, because IR spectroscopy provide us information about the functional group only, and therefore, and as we know that each functional group has its own specific IR frequency, or what we can call it as IR stretching frequency, or the peak is observed around, peak is, or the signal produced due to that OH stretching frequency. And therefore by knowing this, by giving that specific, and in our previous lecture we have learned, we have seen the stretching frequencies of particular bond, the bond between oxygen and hydrogen, the bond between carbon and hydrogen, the bond between nitrogen and hydrogen, the bond between carbon oxygen double bond, the stretching frequency among that carbon carbon double bond, stretching frequency between carbon carbon triple bond, stretching frequency of the terminal acetylenic CH stretching carbonyl groups gives the important and the prominent peak observed around 1700 per centimeter, which is a characteristic of that carbonyl group, and the OH group gives the peak around 2500, means 2500 to 3600 per centimeter. Broad signal, strong and broad signal is obtained. Sometime there is a free, sometime it is a sharp, sometime that bond is appear as a broad. And why these produce sometime is a sharp, sometime is a broad, depending upon the hydrogen bonding, because hydrogen has the ability to form the hydrogen bonding, and generally we know that there are two kinds of hydrogen bondings are present. One is a intramolecular hydrogen bonding and another one is a intramolecular hydrogen bonding. Intermolecular hydrogen bonding means what? Intramolecular hydrogen bonding means what? Intermolecular hydrogen bonding means the hydrogen bonding occur between a two molecule, maybe as a same or different, intramolecular hydrogen bonding, it means that the hydrogen bonding occur within the molecule. So that type of the hydrogen bondings are known as the intramolecular hydrogen bonding. And now here, look at here OH stretching frequencies. There the prominent peak or the significant peak observed here due to that OH is near about, let us see here, 3400 per centimeter. And another peak, in addition to that, one peak is observed. This is a broad, or what we can call it as a peak is observed. And here in this case only one peak is observed around is 1100 per centimeter due to the CO stretching frequency. And here in ethanol two peaks are observed, or two peaks are seen here, one around 1100 per centimeter and one around 1100 per centimeter. While answering this question, the alcohol produce the two peaks, the appearance of absorption peak at 3400 per centimeter shows presence of OH stretching frequency, whereas in addition to this, the peak appear around 1100 per centimeter is due to CO stretching frequency. So these are the two prominent peaks observed in alcohol, whereas if you observe the spectra of ether, you will find there is only one peak, one absorption peak appear near 1100 per centimeter due to CO stretching frequency. So in this way, the peak around 3400 per centimeter or above 3200 per centimeter is absent in case of the ether. Ether gives only one signal, one band is appear, whereas alcohol gives two bands or two signal or two peaks that clearly indicate that alcohol is present in the given compound. So in this way we can easily distinguish the alcohol from ether. So that is a main point you have to discuss over here. Let us see another discussion regarding this. Higher absorption of alcohols and phenols show strong and broad absorption, broad, B-R-O-A-D, broad, strong and broad absorption band in the range 3200 to 3600 per centimeter. And due to OH tracing, this is due to OH stretching frequency. This band is appear due to OH stretching frequency. Another strong band due to broad band due to CO stretching appear in the region 1000 to 1200 per centimeter due to CO stretching frequency. The exact frequency depends upon the nature of the alcohol, and as we know that the alcohols are further divided into three different groups, or there are three classes of alcohols. We know that alcohols are the organic compound which having general formula ROH is known as alcohols, where R may be aliphatic or aromatic and OH is a functional group. When it is attached to the aliphatic compound, it is termed as alcohol, whereas when it is attached to the aromatic compound, that organic compound are known as phenols, and that alcohols are further classified into three types. Number 1, primary alcohols. Number 2, secondary alcohols. Number 3, tertiary alcohols. These are the three main classification of alcohols: primary, secondary and tertiary. Primary alcohols, the CO stretching about 1000 and 1500 per centimeter. Secondary alcohol CO stretching about 1100 per centimeter. Then tertiary alcohols CO stretching about 1115 per centimeter. If you observe here, primary CO stretching 1050 per centimeter, secondary it is around 1100 per centimeter, and tertiary it is around 1115 per centimeter. These all are the frequencies are shown over here. If you observe these figures, you can clearly observe the trend of these frequencies. If you move from top to bottom, at this particular case, the higher frequencies are increasing. This is a general increasing trend is observed when we move from primary to secondary to tertiary, and by remembering this trend, we can easily distinguish whether the organic compound is a primary, secondary or the tertiary alcohols. Then aromatic alcohols, CO stretching frequency about 1230 per centimeter. If aromatics are there, 1213 per centimeter. From that we can easily identify, or we can easily recognize what type of the functional group present in the organic compound. The OH, CH and CO stretching frequency peaks are shown in the various diagrams which are given in the book. Let us see one. Now here is a ether. They show CO stretching between 1100 to 1300 per centimeter, but they can be easily distinguished from alcohols as the OH stretching frequency in the region 330 200 to 36 100 per centimeter will be absent in ether, and by comparing, by giving this type of the signal due to stretching frequency, we can easily distinguish alcohols from ethers. So let me give how the IR spectra are seen in the, if you observe the IR spectra, we have a IR spectrophotometer machine in our laboratory. Now let us see, suppose this is a generally graph representing over here. Here is the absorption. A stand for absorption versus wave length, you can call, or frequency. Here may be as a wavelength generally, and here is a frequency in terms of per centimeter, mu in terms of per centimeter, and here is a wavelength, that is in generally micron, 2.5 to 16 roughly, and here generally the wave frequencies are 4000 to 625 per centimeter. And now if you see here, one of the compound I am showing over here, CH3, then CH twice 2, CH2, C triple bond C and H. This is one of the compound where if you run these spectra, and the spectra looks like this of this compound, it will be like this. Then there may be this type of the, then it goes here maybe one sharp peak, and then it goes like this. Then it may be this type of the spectra you can see here. If you see here, I am circling it, one circle over here, that is a recognizable or the prominent peak is observed here. Now look at this one. This is due to the, this peak is due to the CH stretching. This is due to the peak is appear around 3300 per centimeter, which is due to the CH stretching frequency here. Acetylenic CH stretching frequency here, triple bond CH. And now this is observed due to the carbon-carbon triple bond, which is around 2150 per centimeter. These two prominent peaks are observed, and this is due to the CH stretching frequency, and CH stretching frequency which is a common to all organic compound. So it is not the useful for the organic chemist point of view, because every organic compound produce these peaks at this region. But the prominent peak are, one is seen over here 3300, another one is here due to that 3300 per centimeter, and one which is at 2150 per centimeter. Sorry, here is something is, I am showing exactly opposite here. 3300 terminal acetylene shows the peak around 3300 per centimeter, 3300 per centimeter, whereas the carbon-carbon double bond, the peak is appear around 2150 per centimeter. These are the two prominent peak observed in such a type of the organic compounds. So rest of the thing, I think we have discussed these. Now when let us see another one, which is for the N-butanol. Suppose we have a compound here like this. Let us see another spectra I am going to show you over here, then you can clearly understood what does it mean. Suppose here the CH3 CH2 twice CH2OH. Suppose as this is a general compound N-butanol. Let us see how N-butanol can produce the signal here. Let's see the spectra which you can see very clearly here. The broad spectra will be observed here, and this is due to the CH stretching frequency. Another peaks are looks like this, something like this. But here if you see this or if you observe this spectra carefully, here very prominent peak I am circling here. This peak is appear around is 3400 per centimeter. That clearly gives or indicate the presence of OH stretching frequency. This is over there, and therefore this is a prominent peak is observed in that particular organic compound. Another one peak may appear around here somewhere like this. This is due to the CO 1100 per centimeter. These are the two prominent peak you can see here. One due to the OH stretching frequency, and the another one is due to the CO stretching frequency, or we can call it as a 1050 per centimeter. That clearly indicate that this compound is a primary alcohol, and by knowing the values like this we can easily find out. I think with this let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.